Good morning, guys. As we are starting with general pharmacology this week, we'll see about biotransformation today. So first, these are the topics we'll cover under biotransformation. So first, we'll understand the concept throughout the video, and at the end of the video, we'll see how to write in the exam when this question is asked. So when the biotransformation, so under this, we'll see about what is biotransformation. Before starting with any topic, we must know what it is, right? So what is biotransformation and what is the aim of the this process. Anything has a purpose, right? So why biotransformation occurs in the body, and then we'll see about where it happens. For understanding why it happens, we'll answer where it happens, and then the types. There are two types of reactions that takes place under this, phase 1 and phase 2. We'll see about the types, and for the types to occur, for biotransformation to occur, we need enzymes and all that, right? So that we'll see under the topic enzymes. So after knowing about the enzymes which perform that function, we have to see about the enzyme inducers and inhibitors, the regulation, how it is regulated and all that, and we'll come to the end of the topic. Okay, first, what is biotransformation? So as the name itself suggests, biotransformation. Idhiliyume and the name the answer will be there. So transformation, we know that it is a change. So what is the chemical alteration that is being done to the drug? So actually pharmacology has two branches, pharmacokinetics and pharmacodynamics. Pharmacodynamics is what the drug does to the body. So for example, we have fever and we take paracetamol, something it is doing to our body, only then the change we can observe, right? So what is the drug doing to the body? Pharmacodynamics, dynamics, drug, you can remember like that. And pharmacokinetics is once we take in the drug, the body does some changes to the drug. It absorbs, it metabolizes it, it excretes it. So what is the body doing to the drug is pharmacokinetics. So this biotransformation will come under the topic pharmacokinetics. So that we will see. So biotransformation, as the name suggests, it's chemical alteration that is being done to the drug. So why it happens, why the drug has to be metabolized. For example, we'll take the same example. When we take paracetamol for fever, at a point the action of the drug has to be terminated. It can't prolong its action beyond the point being required. So in order to terminate that action, the drug is being metabolized in the body. So termination of the action of the drug is the purpose of the transformation. So we may think that termination means an active drug, it is being converted to inactive drug, but it is not the case. So it could be an active drug being converted into an inactive drug, or an inactive drug can be converted into an active form, or an active form can be converted into active. So why it actually happens is, the lipid soluble, the drugs are lipid soluble. Only if it is lipid soluble, it will be absorbed from, once we take it, it will be absorbed from the intestine. So once, as long as it is lipid soluble, it will be revolving in the body only. So once it has been converted from lipid soluble to water soluble, the drug will no longer be absorbed from the renal tubules into the body, and it, for example, active form can be converted into an inactive form. Most of the drugs undergo this process only. Or an inactive drug form can be converted into active form. Even in our body, for certain purposes, it is secreted as a pro-drug, even pro-insulin, pro-renin. So like that, it is secreted in the inactive form because it may be more stable than the actual active form. So it may have more bioavailability or more absorption. So because of that, it is given as a pro-drug. And in the body, it is metabolized to convert into an active form. So there are so many examples for that. And an active form can be converted into an active form. For example, a sedative diazepam we take, it is metabolized into oxazepam, which is in turn active. Both are active forms only. So we'll give the list of the drugs at the end of the video. So first we'll see the concepts, then the drug list. So drug list is not actually necessary for the university exams, but for MCQs it's really important. So we'll see at the end. And another one point which must really understand is that elimination is not equals to excretion. Both are different. See, once the drug is being taken, as we see under pharmacokinetics, first is absorption. First it has to be absorbed from the intestine. So that is the first process. Second process is the distribution, how it is distributed from as it is observed, how it is distributed. Next is metabolism. and then it is elimination, or then it is excretion. So you can remember like ADME, like ADMK, so we can remember is ADME. So absorption, distribution, metabolism, and excretion. So why excretion is not equal to elimination? So elimination means to terminate the action of the drug, as we have already seen. So in order to eliminate the action of the drug can either be metabolized. For example, a rat comes into our home, we can either kill the rat or we can chase away the rat from the body. So that is what. So in order to eliminate the action of the drug, we can either metabolize it into an inactive form or we can excrete the drug from the body. So elimination includes both metabolism plus excretion. Both comes under elimination. Okay, so excretion means throwing the drug out of the body. So elimination is the termination, so it includes metabolism as well as excretion. Topic is where it happens, where the biotransformation happens. As we all know that most of the metabolism occurs in the liver, here too most of the drugs are metabolized in the liver, so hepatic metabolism. But there are certain extra hepatic mechanisms also where the metabolism occurs. So you can skip this for university exams, but for a practical purpose it is really necessary, because see, there is an application. Extrahepatic means it could be anywhere apart from the liver. So, for example, in plasma, we have plasma esterases, plasma pseudocholinesterases. We would have seen it already, or Hoffman elimination. So, plasma esterase, as the name suggests, these two drugs are present in the plasma, okay, in the blood. But Hoffman elimination is there is no need for any enzymes, there is no need for any organ. Once the drug has been taken, and the elimination of the drug is based upon its molecular rearrangement. There is a structure to the drug, so that structure will be altered by itself so that it becomes inactive. So it doesn't require any enzymes, it doesn't require any organ at all. So the application is, for example, esmol, we will see in subsequent chapters, beta blocker esmolol, so which is the shortest acting beta blocker. Why it is shortest acting? Because it is metabolized by plasma esterase, and hence, see, it is taken into the body, it comes to the blood, in the plasma it is present, so it will be metabolized faster than hepatic metabolism, right? So it is the shortest acting beta blocker. Like the same, the shortest acting muscle relaxant is succinylcholine, because it is metabolized by plasma pseudocholinesterase. And Hoffman elimination, why it is important to know is, so certain skeletal muscle relaxants such as cis-atracurium and atracurium undergoes Hoffman elimination. So in case of patients who has hepatic failure, so liver failure, we can, the safest skeletal muscle relaxant we can give is cis-atracurium, because it is getting metabolized by Hoffman elimination, by molecular rearrangements. It doesn't require liver. So that is the purpose of knowing these. Okay, after having understood what is biotransformation and why it happens and where it happens, let's understand how it happens, how the process actually goes on. So if we answer these 4 questions, almost all the topics in the medicine will be covered. So we'll see how it happens. So there is 2 types of reactions. By phase 1 reactions are otherwise known as functionalization reactions or catabolic reactions or non-synthetic reactions, because catabolic, as the name suggests, it is breaking the molecule, it's breaking the drug into smaller groups. And non-synthetic reaction, because there is not a new molecule is being synthesized here, it is breaking, it's just breaking reactions. And functionalization reaction, why? Because see, the whole purpose of phase 1 reaction, so here the compound is being broken down so that the functional group is being exposed, that's why it is functionalization. And in phase 2 reaction, a molecule is being attached to the drug, so that is conjugation, that's why it is known as conjugation or synthetic reaction, because a new compound is being synthesized here by conjugating with the molecule. So why it happens? Because so the conjugating molecule is a polar one. Basically, it is negatively charged, so that when it is getting attached to the molecule, it not only makes the molecule bigger in size, and also it makes it polar. That means water soluble. So it will not be reabsorbed from the renal tubules, so that it will be excreted. So that is the whole purpose. The whole purpose is to make a lipid soluble compound into a water soluble or a polar molecule. So then we can understand this by say a new molecule which is negatively charged is being attached with it so that it becomes water soluble. So the phase 1 reaction is like a glue between this both, because the functional group has to be exposed from that compound in order to get attached with the conjugating molecule. The conjugating molecule could be anything, an acetyl group, or it could be a methyl group or sulfate group. So it acts like a glue, the functional group. So phase 1 reaction exposes the functional group, and phase 2 reaction conjugate a molecule with it, so that finally we get a bigger water soluble compound, so which will be eliminated. So that is the purpose. So phase 1 reactions you can understand with the mnemonic or chat. So which is oxidation, reduction, cyclization, hydrolysis, aliphatic or aromatic dehydrogenation, deamination, dehydrogenases. So it's not very important to know the examples, but like remember it with the mnemonic or chat. So oxidation, reduction, cyclization, hydrolysis, aliphatic or aromatic hydroxylation, deamination, dehydrogenation. So for each reaction there are certain enzymes which help this. For example, for oxidation we'll be seeing in the further topics that cytochrome enzymes are helping for oxidation, and for reduction, for example, for dehydrogenation we would have heard the name alcohol dehydrogenase. For oxidation we will see about cytochrome P enzymes in the further topics. And for example, reduction, so we know oxidation is adding oxygen or removal of hydrogen. So these processes are being done to expose the functional group. So either the linear compound can be made into cycle form or decyclization. So that is a cyclic compound can be converted into a linear form. So somehow it has been broken down so that the functional group is exposed, and in the second phase to that functional group a conjugate molecule is being added. That molecule can be a glucuronide or glutathione, acetyl or methyl. Based upon that the name changes. For example, adding a methyl molecule to a functional group is methylation. So based on that, for everything that particular enzymes also will be based on it. For example, adding sulfate, the enzyme which helps is sulfate transferase. So that will end with the name transferase, because it is transferring that compound into this molecule. For example, methyl transferase, N-acetyl transferase, glutathione transferase, UDP glucuronide transferase, you would have heard the name. So these are we can remember the phase 2 reactions with the mnemonic GAMES, GAMS, and phase 1 reactions with the mnemonic or chat. So these are the examples of phase 1 and phase 2 reactions, and we'll see about each reaction in detail subsequently. Especially the most common phase 1 reaction is oxidation, and the most common phase 2 reaction is glucuronide transfer. And another important thing is, so for all these reactions we have seen that enzymes are required. Phase 1 reactions are mediated through microsomal enzymes, and phase 2 reactions are mediated through non-microsomal enzymes. Now what is microsome? Microsome is nothing but a part of endoplasmic reticulum. Okay, we'll see in detail about the enzymes, but generally phase 1 reactions are mediated by microsomal enzymes, and phase 2 by non-microsomal enzymes, except glucuronidization. It is mediated by microsomal enzymes. So what is microsome? Microsome is a part of endoplasmic reticulum. So if the enzyme is present in the endoplasmic reticulum, that is a microsomal enzyme, and wherever apart from the endoplasmic reticulum the enzyme is present, it is non-chromosomal enzyme. For example, it could be in the cytoplasm, or it could be in the nucleus, anywhere. The speciality is microsomal enzymes can be induced or inhibited, but non-microsomal enzymes cannot be regulated. So that is why it is being divided like this. And phase 2 reactions are mediated through phase. And also another important point is phase 1 reactions. In the phase 1 reactions, an inactive compound can be made active, or an active compound can be made inactive. So basically here we are just adding the we are just exposing the functional group, so it could be turned out into an inactive or an active form. But here in the phase 2, because since we are adding a big water that is polar molecule into the molecule, so here it will be only inactivation of the compound, no activation except morphine. Okay, so here so these are the differences you can write in the exam. So first we can write the examples of phase 1 and phase 2 reaction, what it is about. First, synthetic or non-synthetic, based on that one point we can write what is that reaction is about, and then we can write the examples. And thirdly, phase 1 by microsomal, phase 2 by non-microsomal enzymes except glucuronidation. And fourth point is inactive to active or active to inactive. Here only inactivation except morphine. And fifth most important point is the most common phase 1 reaction is oxidation. The most common phase 2 reaction is glucuronidation. Between microsomal and non-microsomal enzymes. So microsomal enzymes are present inside the endoplasmic reticulum, smooth endoplasmic reticulum. Non-microsomal enzymes outside the smooth endoplasmic reticulum. Most of the drugs are metabolized by microsomal enzymes. Some of the drugs undergo by non-microsomal. So example, CYP enzymes, cytochrome enzymes, UDP glucuronide transferase. These are microsomal enzymes. So phase 1 reactions are metabolized by microsomal. Exception is UDP glucuronide conjugation, which is a phase 2 but still is undergoing microsomal. So here most of the phase 2 reactions are metabolized by the non-microsomal. Genetic polymorphism is shown by both of the enzymes, microsomal and non-microsomal. The most important distinguishing feature is microsomal enzymes can be induced or inhibited. So we have seen, right, so the inducers, inhibitors, so that can be induced or inhibited. Non-microsomal enzymes cannot be induced or inhibited. They are present outside the endoplasmic reticulum, which cannot be inhibited or induced. Whereas microsomal enzymes are present within the endoplasmic reticulum that can be induced or inhibited. So that is the importance of knowing the difference. Okay, next we'll see about the CYP enzymes. So first of all, nomenclature, why it is named so. These enzymes are CYP 450 enzymes. So CY stands for cytochrome. So we all know that cytochrome is an heme protein. So why there is a need for heme here? Because we have seen that CYP enzymes are mainly mediating the oxidation process. So obviously it has to carry the oxygen, right? So we all know that heme is mainly for the carrying of oxygen. So here also that is the purpose of cytochrome here. And P denotes a pigment which is present in that enzyme that absorbs the light at the maximum at the wavelength of 450. That's why 450 nanometer. That's why it is named as CYP 450 enzymes. So there are different kinds of enzymes, cytochrome enzymes in the body. So it is named accordingly. So for example, if it is CYP 3A4, 3 denotes the family of that enzyme, A denotes the subfamily, and the 4, the last letter, denotes the gene isoform of that enzyme. So this is the nomenclature. So family, subfamily, and gene isomer. So cytochrome is the heme protein which carries the oxygen. So pigment which absorbs the light at the maximum wavelength of 450 nanometers. So this is general about the CYP enzymes, and there is a tabular column given in KDT. So for CYP enzymes and inducers and inhibitors. So you need not know everything, but the important enzymes you must know. For example, CYP 3A4. So it's the most important enzyme because almost like 50% of the drugs are metabolized by the CYP 3A4. So you need not remember the drugs because it is huge, right? 50% of the drugs, like almost asthemazole, estrogen, mifepristone, like many drugs are metabolized by this. And next to that is CYP 2D6. It metabolizes almost 20% of the drugs. So next is CYP 1A1. So you can remember, like as soon as we get up in the morning, we drink coffee, right? Coffee or tea. So 1A1, it metabolizes theophylline and caffeine. We all know that theophylline is more in tea and caffeine in coffee. So CYP 1A1 metabolizes that. And the next CYP 1A2, it's not important, but if you want paracetamol, Tacrine, carbamazepine are metabolized by this. It's not that important. Next is CYP 2D9. It is really 2D6. Sorry. So 2D6, as we have seen, it metabolizes almost 20% of the drugs. You can remember, like 2 denotes, see, alpha, beta. So beta is second, right? So 2 beta blockers. So it is important. So 2D6 metabolizes 3, 4 we need not remember because almost 50% of the drugs. So 2D6. So if you remember the rest, if they ask some other drug, you can put it in 3A4. So 2D6, 2 you can remember beta blockers, alpha 1 beta. So beta blockers that will we will see in the next chapter. So everything that ends with all like that. And D, you can remember as antidepressants. It's very important. All the antidepressants, antipsychotic drugs are metabolized by 2D6. Opioids and antiarrhythmic drugs are metabolized by 2D6. And then 2C9. So 9, if you know mirror image, if you put like P, right? So phenytoin and warfarin. It's very important. So phenytoin you can remember it is actually an anti-epileptic drug. So brain is very active during epilepsy, and war like that you can during war like that you can remember. So phenytoin and warfarin. 2C9 and 2C19 is C19. So that means it's a huge number than 9. So for simply 9 you have to remember that P. So C19 clopidogrel, a big name. So C19 clopidogrel, and clopidogrel, P is coming, I is coming, right? So PPI. So that is proton pump inhibitors. It is also very important. Why it is important? Because it has lot of applications. So and then finally CYP2E1. 2E1 alcohol and paracetamol. So 2E1 you remember like the drugs related to the liver. So paracetamol we all know that excess in quantity leads to hepatotoxicity, and also alcohol obviously affects. So 2E1 metabolizes alcohol and paracetamol. So these are the important drugs we must know under each enzyme. We'll see about enzyme inducers and inhibitors. So what is the concept is, say enzyme inducers. Don't think inducers will increase the drug concentration, because see it is enzyme inducers are substances that induces the enzymes. So for example, a drug is being metabolized by an enzyme to its inactive form, ultimately it is eliminated. So when the enzyme is induced or activated, what will happen? The elimination will be more. So if the drug elimination is more, the plasma concentration will decrease. So that will lead to drug failure. So if it is induced more, so enzyme induction leads to drug failure because it is inducing the enzyme that is metabolizing the drug. And on the other side, enzyme inhibitor. So enzyme inhibitor are substances that inhibits the enzyme. So when the enzyme that metabolizes the drug is inhibited, that means the